My name is Claire Tomlin, and this is Module 7 of a series of modules we're doing for the course EE221A at Berkeley, Linear System Theory. And in this module, we're going to introduce the concepts of norms and normed vector spaces. So we've talked about vector spaces, and we've talked about maps between vector spaces. Basically, a norm is a special map between vector spaces, which takes elements from a vector space V over a field F and maps those elements to the positive real line. Okay, so these are positive reals, and we use the notation, these two parallel bars, to indicate the operation of a norm. The dot here just means that that's where that element of the vector space goes. So it takes an element of a vector space and gives us a positive real. And so we call a normed vector space to be such a vector space V which has a norm defined on it. Okay, now the definition of a norm is quite general, yet quite specific. So what does that mean? Well, we have to, it is a map, and it has to satisfy these given properties. So a norm, which is, we'll use this notation, so it maps V to R plus, satisfies the following properties. The first is called the triangle inequality, and that is that if you look at the vector sum of two vectors, V1 and V2 and V, and you take the norm, then that's going to be less than or equal to the sum in R plus of the norms of the individual vectors themselves. And that's true for all V1 and V2 in the vector space V. The second is that if you look at the norm of a scalar, alpha times the vector V in the vector space, then that's equal to the absolute value of the scalar times the norm of the vector V. And something that I forgot to mention that I should mention here is that this norm is operating from the vector space to the positive reals, but the understanding is that that vector space, the normed vector space, in that the associated field has to be either the real numbers or the complex numbers. So this terminology, the absolute value, has meaning. It's either the absolute value of a real number or the corresponding absolute value, the magnitude of a complex number or a real number. So here, for a normed vector space, we restrict ourselves to be F is either, the field is either the real numbers or the complex numbers. Okay, and then back to our properties. The third property is that if the norm of a vector evaluates to 0, then that's equivalent to the vector itself must be the 0 vector in the corresponding space. Okay, so the norm has to satisfy these quite specific properties. And so given a definition of a map which satisfies these properties, it is a norm. But if somebody gives you a candidate norm, you have to be able to check that it is a norm by checking that it satisfies these three properties. Okay, some examples. So examples that we're familiar with. Probably the most familiar are examples in what we call the vector norms. So if the field is either the reals or the complexes, then we can think about Rn or Cn over the field R or C. And then we can look at some norms that we use all the time. So the first one is typically called the 1 norm or the L1 norm. So the 1 norm on a vector x is equal to the summation from I equals 1 to n of the absolute values of its components. Okay, so here x is a vector in Fn, and x is simply x1 up to xn. Okay, so it's the sum of the absolute values of its components. And then we can go on and talk about other norms. So this is probably the most familiar, the 2 norm, which is the summation from I equals 1 to n of the squares of the individual elements, and we take that whole thing to the square root. So that's called the L2 norm. In general, we can talk about a p norm. So that's the summation from I equals 1 to n of xi, the elements to the p, and then we take the pth root of that summation. And then finally, we often use the infinity norm, and that's just the max absolute value. So you look at all of the elements, you take the absolute value of all of the elements and choose the largest one there. So the max over I equals 1 to n of the absolute value of xi. Okay, so these are standard norms that we use all the time in Rn. What about other vector spaces? Well, we can think about matrix norms. So vector spaces which consist of matrices, and we can construct norms on those matrices. So, for example, here's more examples. So we're going to consider matrices A, and they don't have to be square. So we'll say belonging to Fm by n. Okay, where F is either the reals or the complex numbers. And so here are some possible matrix norms. This is typically called the A norm. So it's the summation from over the rows and columns, I equals 1 to m, j equals 1 to n, of the absolute value of aij. We have something that's called the Frobenius norm of a matrix. And that's the, if we take the summation, I equals 1 to m, j equals 1 to n, aij squared all to the 1/2. That should be a bracket. That's called the Frobenius norm. And here's another one, the B norm. Okay, so this is sort of dry. It's just a list of norms. I equals 1, the maximum over the rows. So that should be over the elements of the rows. Max over I and j. So this goes from 1 up to m and 1 up to n of aij. Okay, so these are matrix norms. They work, they satisfy the properties of a norm, you can check them, but we don't use them so much. They're not so useful. In fact, in this course and a lot of linear systems, we tend to use another definition of norms for matrices, which is norms that come out of something called the induced norm. And we're going to be talking about that in the next module. Okay, but let me go on. So I gave you these, but then I told you that we don't tend to use them so much. So let's think about more spaces. So this vector space or the space of matrices, we talked about standard vectors. What about function spaces? We can define norms on function spaces. And there are some standard ones that we use all the time. So here, examples of vector spaces which are functions. So functions. And let's use functions f of whatever, our argument. And so we could think about our argument as time, for example. So continuous functions over a time interval t0 to t1, mapping over to fn. Okay, so a vector space that we've talked about. One possible norm on that function space is called the one norm, and that's just the integral from t0 to t1. So it's defined in terms of the domain of the function of the norm of f of t dt. Okay, so this is a little bit interesting because f evaluated at t, once we instantiate f with t, it gives us a vector in fn. And so what we mean here is this norm around that vector in Fn can be any of the norms that we talked about previously for norms in Fn. This is called a one norm, but this doesn't actually have to be the corresponding one norm in Fn. It could be any of those vector norms. But the important thing here is that for a particular time in t0 to t1, f of t is a vector, and so that is a vector norm. And so now in order to construct the function norm, we take that vector norm and we integrate over the time interval. That's called the L1 norm for functions, so the L1 norm. We can have one that we use all the time is the 2 norm for functions. So F2 is simply what you might expect from what's been given, the integral from t0 to t1 of f of t norm squared dt all to the square root, all to the 1/2. So that's the L2 norm. And when we think about functions which are finite in the L2 norm, we typically call that space L2, so the space of square integrable functions. And then finally, another popular one in the function space is the infinity norm. And so that's equal to the max value that f of t takes on, or the max vector norm that f of t takes on over that whole interval. Okay, so we've talked about vector norms, we've talked about matrix norms, and we've talked about function norms. So something a little neat to think about now is the following, is that if we look at different norms and we ask, how are those norms related to each other? So if you have a vector that's finite in one norm, do we know anything about its value in terms of another norm? And so we have this really neat property or really neat relationship called equivalence of norms. And that states the following, that 2 norms, and I'm just going to use generic notation, A and B, norm A and norm B, on the same vector space are said to be equivalent, if one can be bounded with respect to the other. So we write that as if there exists constants, and I'm going to call them ML and MU for lower and upper bounds, and those are positive constants, positive reals, such that the following is true. ML times norm VA is less than or equal to VB, which is less than or equal to MU VA. So if vector v is finite in the B norm, then by this relationship, it's going to be finite in the A norm as well. And moreover, there are bounds that ML and MU, which kind of give bounds on the differences between the value of v in those norms. And so we can come up with some nice relationships then. So example, if we look at the vector norms in Fn, we have the following. We have things like the infinity norm on x is less than or equal to the 1 norm, which is less than or equal to n times the infinity norm. So here x is a vector in Rn, or Fn, Cn, it doesn't matter, and n represents the dimension of that vector. And so this kind of thing is very easy to prove by just looking at the definition of the norms. So for example, if you wanted to prove that example, you could say, well, okay, x infinity is the maximum value of the absolute value of the elements of x. And the 1 norm, x1, is just the summation from I equals 1 to n of xi. And so if we suppose that we pull out the maximum value, so suppose we say, well, that's equal to the max over I of xi plus everything else. So the summation from I equals 1 to n, but let's take away the jth element. Let's suppose that the maximum occurs at the jth element. So max over I of xi happens at I equals j. So I've pulled that one out, and then I've put everything else in this summation here, xi. Then we can quickly see that this relationship holds. Therefore, we have that the infinity norm on x has to be less than or equal to the 1 norm. The 1 norm, just because we've got all this extra positive stuff here. And then if we wanted to show this relationship here, that the 1 norm on x is less than or equal to n times the infinity norm of x, we'll just, we can look at the 1 norm. So let's write it out as x1 is x1 plus x2 plus xn, to make it a little clearer. And so that's going to be less than or equal to, so each of these elements here is less than or equal to the max. So that's less than or equal to the max over I of xi plus this one, the max over I of xi, plus, and all the way up to the nth element, plus the max over I of xi. So I've just replaced each of them with the upper bound on the max. And that's just equal to n times the max over I of xi. Okay, which proves this relationship here. So typically these relationships here are easy to prove. Okay, and we'll conclude with basically if we look at these norms, in particular in Fn, we can show that all of the norms that we've discussed are equivalent. So all of the vector norms in Fn are equivalent through this relationship, meaning that you can derive these bounds ml and mu, which can relate the norms on Fn one to the other. Okay, so what we've done today in this module is we've taken a vector space, we've defined a normed vector space in terms of a map, which takes elements of the vector space and maps it over to the positive reals, which has 3 properties. And then we've looked at examples of norms, typical examples that we look at all the time. In the next module, we're going to be talking about the very interesting concept of induced norms. So norms that are induced by some kind of function operation. And that will conclude today's module.